minutes introduction untadi kada. Imran.
Sir.
You can start.
Right, sir. Thank you very much. I, Mohammad Imran, Assistant Professor, Coordinator of FDP, Emerging Trends and Challenges in Electrical Engineering, on behalf of our organizing team, wishes you a overwhelmed good evening to one and all. Respected dignitaries, patron of our faculty development program, Dr. C.H. Srinivas Garu, Principal of Vaageswari College of Engineering, Convener of FDP, Dr. M. Ramesh Garu, Professor and Head of EEE Department, and our today's distinguished speaker, Dr. V. Rajagopal Garu, Professor, Department of Electrical Engineering, Kakatiya Institute of Technology and Sciences, Warangal, coordinators of FDP, and all my dear participants of FDP. On behalf of EEE Department, Vaageswari College of Engineering welcomes you all for day 5 of FDP, titled on battery charging of grid interfaced solar PV system for electric vehicles. I am honored in delivering the introduction of our today's eminent speaker, Dr. V. Rajagopal sir. Sir has received AMIE electrical degree from the Institution of Engineers, India. Sir has completed MTech degree from Uttar Pradesh Technical University. Sir has obtained the PhD degree in the Indian Institute of Technology, Delhi. Sir is presently working as professor in Kakatiya Institute of Technology and Science, Warangal. Sir's area of interest includes power electronics and drives, renewable energy generation, applications, facts, and power quality. Sir has attended more than 54 international and national. Sir has published more than 54 international and national journals and has attended many number of conferences held at India and at abroad. Sir is fellow of Institution of Engineers and life member of the Indian Society for Technical Education. On behalf of our department and college, I express my sincere thanks for Dr. V. Rajagopal sir for accepting our invitation, and we are admired to have you in this session, sir. We welcome you, sir.
Thank you, Mr. Imran. Thank you for your
welcome, sir. Welcome, sir. I request sir to continue the session.
Thank you, Mr.
Welcome, sir.
So today's topic is basically we are dealing with, earlier I have given this topic as the solar interfacing to grid. So today's date, as we are seeing, basically the solar renewable energy is playing a bigger role, like wind, then comes your solar, then small hydro. So many of the renewable energy sources which are very prominent is the solar energy. And so previously whenever I had given this topic, the topic was given as a grid interface solar PV system. That was the topic which I had given. Now today's topic is what? So if I want to have today's date, the electric vehicles are coming into market very fastly in Western countries, and in future we can see a lot of electric vehicles into our Indian market also. Then it becomes that every place it becomes that battery charging stations becomes an essential place. So what I thought is, so how to go with this topic. So we already worked on the previous topic. So this is the extension of this. So the first thing is what? Why should we go for this topic? What is the necessity going for this topic? So there is an increasing demand for energy day to day, and the prices of fossil fuels like petrol and diesel, it's going up and up. So that's the basic reason. And second is the coal accounts for 52% of prime energy input. The coal basically sector in 2019 and expands to 68% by 2050. By 2050, we are feeling that the coal will be the reason. So seeing the geography and all, the total fuel, whatever the fuel will be there, fossil fuels will be exploited. The coal will be exploited by 2100. Now today is 2020, another 80 years down the lane, we find the fossil fuels will not be there in market. Then what happens? We have to go with the renewable energy sources. So whenever we are thinking of renewable energy sources, what all the issues will come? So whenever we are connecting, what happens? We cannot generate the renewable energy things and keep it with us. We have to connect to the grid. So whenever we are connecting to the grid, the biggest problem comes is the power quality issues. How you interconnect it and what are the power quality issues. So this has was prompted to take this topic. So here, whenever we see this, first one, what all we going to study in this? First one is what we are going to study about the D-STATCOM. Why we are going to study the D-STATCOM? Whenever we see the also circuit diagram, we'll understand. So whenever we are doing, what are the problems whenever we are going to this topic is the voltage profile of the grid is not very good. So even if you can see in the evening also, you find the voltage of the grid is even going up to even less than 200 volts. And next one, as we are using lot of power electronics devices, the power quality is going to go down. How the power quality, the THD of voltage and current is not that good. So automatically the power quality is going to go down. Next one is what? Load balancing. If I am not loading the three phases of the load in a balanced manner, so what happens? There is a large neutral current flowing. That is one thing. Aspect load balancing is whatever the load will be balanced in all the three phases, but the source will be balanced. That is our this one. And safety precautions while interconnecting. That also we are going to check. Next, whenever we are looking into the electric vehicles batteries, we are not studying of the electric vehicle. Only we are charging about the charging stations. Today's date, the electric vehicles are having a batteries of 24 volts, 48 volts, and 72 volts. Nowadays, they are saying that 110 volts batteries are also there in the picture in the electric vehicles. So it becomes essential that we require a DC. We require a DC. It should be stabilized DC, and at the same time, we should be giving to the electric vehicles. That's the idea basically. So how we gone through this? If you just look at this diagram, the total, I will say, the diagram looks like first we have the grid. You just see the grid. This is the grid, three-phase grid, and it is connected to some loads. It's connected to some loads, and I've taken some loads as nonlinear loads. The nonlinear loads are being represented by something like a three-phase bridge rectifier. On the DC link, we have a RL load, large L load and a small R load. So which gives saying that it will become a nonlinear load. So if you check the input currents of all the three phases, you'll find almost a quasi-square waveform. So quasi-square waveform is what? First 30 degrees, there will be no input. Next 120 degrees, there will be a square shape waveform. Another 30 degrees, there will be no zero voltage, zero current. So that sort of waveform is basically called as the quasi-square waveform. So from here, if I look into this, I have a grid, I have a load. So from this, between this and this point is basically called as point of common coupling. I mentioned this point as basically the red lines, and I should have put here also. This is called point of common coupling, where the load is connected to this point, source is connected, and I need one controller, one I will say compensator controller, which is called basically D-STATCOM. This D-STATCOM is operated as with 6 IGBTs. On the DC link, we have a small capacitor, and this is the way it is connected. And we have a small buck converter like this, or buck boost converter, So I can raise or also I can give a required voltage here by operating this to the electric vehicle. So this electric vehicle may be 24 volts, 48 volts or 72 volts. So nowadays they are saying that 110 volts has come into the market. So like this, we require whatever the charging station is there, the charging station will be connected to this point, two dots at this point. This is the way how it is being connected. And I'm saying that we are not only supplying from the grid, but we are also supplying for what? The solar panel. So solar panel is being connected through a diode. So this diode is being kept. Make sure that power only flows from solar panel towards the grid, not from the grid towards the solar panel, because the cells are very small voltage in nature. Whenever the grid voltage flows into the solar panel, it may damage the solar panel. So that's why I kept a diode, making sure that power doesn't flow in the reverse order. Only the power flows from the solar panel towards the this one. So I have put an MPPT algorithm. So MPPT algorithm is what maximum power point tracking algorithm, which makes sure that whatever the solar irradiance is there, it is going to have the maximum power. So for this, what I have done, solar power may be large, solar power may be so. I'm taking a DC-DC converter, applying the MPPT algorithm, putting the power to the this DC, I would say DC bus. This is the place DC bus, from where we can put a buck boost converter or one more DC converter to give. Either I can use the same DC converter, but generally what happens, the voltage of this DC bus is around 3 to 400 volts, but the batteries are charged with 24, 48 and 72 volts. So I require a small a buck converter here, a small buck converter here. This is the, so what I'm doing in this, first thing is what I'm operating up to this point. If I see, it is a D-STATCOM, and here this is a solar interconnection, and I have a small buck converter, buck boost converter to give it to the electric vehicle. So this is basically what we are working is solar. I'm connecting to the grid. At the same time, I'm also charging the battery of the electric vehicle. So while doing all this, what all the issues we are able to come is we are able to get a power quality issues. Power quality issues may be different voltage power quality issue, current power quality issue, PhDs. You have a load balancing, then you have say neutral current compensation. Lot of things will come into play in this. So we are going to get one by one into the picture. So first we'll study up that one aspect, and one more thing also I put small things in data. It's a closed loop operation. Whenever we look into that, it's a closed loop operation. Whenever we are talking about a closed loop operation, we use some PI controllers. So PI controllers KPK values are having very difficult to get the exact values of KPK. So many times we publish a paper in international journal saying that this is our work. The first question they'll ask is, so how you tuned your PA controller? So we'll say that Ziegler-Nichols method. So it simply says that generally we don't use, but generally say hit and trial method. It doesn't work. Hit and trial method. Generally we do hit and trial methods. So here I have a controller also there. So how to get also, that we'll also talk. So now our very picture today's lecture is what? Solar power I'm pushing into the grid. That's one point. On the also DC bus, I'm charging an electric vehicle with the help of small buck boost converter. This is the basic idea of our work. So whenever we go into the next topic, we'll see what are solar cells. Convert light into small electrical output. The output will be milliwatts output. Convert light into small electrical output, that is basically very small. So which cannot be used. Milliwatt means what? We cannot even use it. So what we'll do? We need a bank or array of cells for useful output. If we want the output in watts, we require a bank of arrays, means panels. If you see one panel which may be kept on your college top, or you can say on a rooftop of your house, lot of panels, lot of small cells are either connected in series parallel connection to make a useful output. So now the big problem with the solar is what? the cost of cells is high, but it is reducing. Even the government is encouraging us to buy the solar panels with a subsidy, and subsidy is given by the government. Efficiency of the cells is only 23%, but it's still improving. It's improving. It's a free of cost. Solar energy is free of cost. Whatever the efficiency is there, we are able to push the power into the grid. So in Kids Warangal also we have a big solar also energy plant. So whenever we are using the solar power, so it will be fed to us. If not, the power will be fed to the grid. That's the basic idea of this one. So whenever you see, whenever we see, many times these solar panels are situated on the rooftop of the buildings. So sometimes it can be used for converting to electricity. Sometimes it can be used for heating domestic as a domestic hot water heater. So this is one of the things. So here, whenever we are looking, solar panels nowadays are being kept like this. Everywhere you see solar panels are kept like this. Even whenever you see some colonies in Mitchell and all, you find these colonies, even total colony also rooftops is of solar panels only. So they are not going to buy, the day will come, we are not going to buy any electricity from the grid. We are only going to generate, and sometimes we are generating more, we are going to feed to the grid, and where we find the grid will pay to the individual. Individual means individual this one. That's the next things going to happen. And next one is what? Like this solar panels. And whenever you see Sardar Sarovar Narmada Nigam Limited, this is in Gujarat, on the canal itself you see the panels are being kept so that the temperature of the panels will be cool. So one of the aspects that where the maximum power will be seen in the coming slides, you'll be seeing lot of analysis on this, why the temperature should be low. And next is what are the terms related to solar cells? First thing is what? Irradiance. First thing is what? Irradiance. Irradiance is what? The amount of useful light falling on the panel, which will be converted into the electrical energy. That's basically the irradiance. Next is the temperature. If the temperature is large, the solar panel is not going to give more electrical energy. That's the thing. Next thing is wind speed. If the wind speed is more, what is going to happen? Wind speed is more. The next thing is water. The temperature will be little less, and it depends on the I will say wind direction also, which keeps the temperature of the panels very, very in the moderate temperature, gives more power. That's the basic idea to understand this. If you see the solar, this one, if you see the IV curves. IV curves is what? The current versus voltage of any panel. If you just study, there are two important points in this. There are two very important points in this. The point on the y-axis, if you just observe the y-axis, this is called the short circuit current. Whenever the panel is being just short circuited, the maximum current which can flow through the solar panel is ISC. And whenever you see if the panel is open circuited, if you measure the voltage which is on the y-axis, which is on the x-axis, which is called open circuit voltage, and this open circuit voltage is basically called as a POC. These are the very two important points. And whenever the voltage, for example, the current goes on increasing, if you draw more and more current, what happens? Current slowly increases. At one particular point, current starts decreasing with the increase in voltage, and after that what happens? Current starts decreasing, and at open circuit currents will be zero, and the short circuit current, the voltage will be zero. This is the curve which can be plotted on an solar panel. Any of the solar panel, we have two things. And the bottom blue curve, you can see the blue curve is basically the PV curve. PV curve is basically the power versus the voltage curve. Power versus voltage curve is what? What is the power developed and what is the voltage across the panel. If I see only at particular point of voltage and particular point of current, we find the maximum power. We are not going to find the maximum power at each and every current direction and each and every voltage level. We are only going to get the maximum power only at a point, the peak of this hill. We can say peak of this hill. This hill basically is called the maximum power, and everybody wants to operate at maximum power point because even the efficiency is less, which makes if I'm not operating at maximum power, the power will go as just waste. If I operate any point at below the hill, I'm talking about this curve looks like an hill, either here or here, the power is not maximum. We have to only generate the maximum power at the hill, and it is the I will say responsibility of the engineer who is working on the solar panels to make sure that always we operate at maximum power. Example, we'll go to the next slide. We'll see example curves on the left side. If you just observe the curves on the left side curves, if you just observe, the curves are taken at 1000 watts per meter square irradiance, 800 watts per meter square, 600 watts per meter square, and 200 watts per meter square. There are 4 types of irradiance. This may occur 200 watts per irradiance in the morning, 1000 watts per meter square may occur in the noon. So this can be in between the values. So if you just observe the things, the current, you see the I will say the IV curve, the current versus voltage curve, the shape of the current curve is completely changed. What is happening? The short circuit current is going to drastically change with the change in the irradiance, but the voltage is varying from 21 to 20 approximately. It is not that big variation. And the right side curves, if you observe the right side curves, the top curve, which we can see is for 1000 radians watts per meters. Second is 800, 600, and 200. If you just observe, if irradiance is large, then the power generation is very large. And while talking with these two curves, I never spoke anything regarding the temperature because this is interlinked to each other. So I am not going to talk. First, we are only going to talk about the irradiance. So what we observed, if irradiance is large, the MPPT will say the maximum power is large. So this is the way how it goes. Right, left side curves are IV curves, right side curves are PV curves. Next goes, if I have keeping the irradiance constant, I'm not changing the irradiance constant, but I'm going to change the temperatures. What is going to happen? First, if I operate with 25 degrees centigrade, 50 degrees centigrade, and 75 degrees centigrade, we have plotted 3 curves. So if you just check, current may be almost the same, but the voltages are varying very large. Voltages are varying approximately 4 volts. 4 volts is a big value in the solar panels and all. So here, this where the voltage should be 22, this fall into is 18 or 17.5. And if you check the, I will say this PV curves, the maximum power is acquired with the 25 degrees centigrade, and the red one with 50 degrees centigrade, 75. What is the general observation is irradiance should be large, but the temperature should not be large. What is the understanding by seeing these two curves? When we go for the previous curve, if I go for the previous curve, we understand that if the irradiance is large, my power is large. Here, if the temperatures are large, then what happens? Temperatures are large, my power is going to go down. So we should make sure that the panels are fixed, wind should flow, temperature should be very less, temperature should not, I would say, be very large. So by this, what we understand is moderate room temperature or little more than the room temperatures, the power, I will say, generated is large compared to the higher temperatures. So this is the basic idea what we are going to get. So here next one is what I got 3 curves. 3 curves. So next one is what if I got 3 curves, the next one is how I will say put the load. If example, generally we say the load is more. the load on the any system is more, indicates that my resistance is less. Simple. Resistance of the system is less. So what happens? It draws more current. Generally, we say more load means what? Not more resistance. More load means what? Less resistance, because always the load is connected in parallel to the any of the voltages. So what happens? If I have less resistance, what happens? It draws more current. If I have medium resistance, something like 0.4 ohms, it crosses through the maximum power point for the blue curve. And if I have 1.5 ohms for a particular application, I'm saying, so it will be, the current drawn will be less. If you see, current drawn will be less. So that means what is the general understanding is what? The understanding is what? If I have maximum power, example I'm saying, I have three curves here. One is blue, one other is green, other is red. For blue curve, if I take 0.4 amps, 0.4 ohms or load, it is just passing through the maximum power point. Immediately, due to less sunlight, I'm saying that the irradiance may be lesser. The curve may come to green line. This also 0.4 ohms is not touching the green line exactly at the maximum power point. If I further reduction in the irradiance or the sunlight, what happens? Even it is not touching this one at maximum power occurs somewhere on the bent portion, not on the flat portion. So here, what is happening? If I put a fixed load on something, if fixed load on something, and I'm irradiance, the sunlight is changing throughout the day, who is going to change the, let's say, operated maximum power point? That's a big question. We'll go to the next one is this is the solar panel, and this is the load. Load is the resistance R, and it's drawing a current IA. If I draw, I will say, solar panel as I will say IV curve for a particular application, this one, for this R, particular given R is 7.2 ohms for a particular application. So this current, I will say, this will touch the IV curve at a point where the power consumption is only 180 watts. I would have operated this curve at this point, the things would have been a different shape. But whenever I operated at 7.2 ohms, so if I see, now I increase the resistance to 6.3 ohms, immediately the power has gone to 372.8 watts, which is much higher than, almost double the value than the previous one. And if I go for the third one, if you just see this one, this 372 is from the PV curve, which say that it is a peak of the hill. And if I go for the three different values, if I say the same curve, same line is touching three different irradiance at three different points, I'll get first one 372.8 ohms, second curve 235.62 ohms, 62 watts, and third one with only 119 watts. That means what? If I am an engineer, I'll never think that I should be operating at 119 watts. I'll be always want to operate at highest maximum power. So if irradiance is going to change, come to the next point, I'll change the load resistance or load thing. It should only operate at the knee point. So who will do this? That we are going to study. So here, if I have, if you just observe the first curve, if I put the resistance of 16.3 ohms, I'll get a maximum power. The second curve, if I put 20.4 ohms, I'll get the maximum power. Third one, if I put 27.0 ohms, I'm going to get the maximum power. Maximum power depends on what is the load current, and load current is there automatically, it adjusts to the particular value. Either current should be adjusted or the voltage should be adjusted so that it operates at maximum power. So if you see the right diagram, it is a diagram which connects to 75, 50 and 25 degrees ohm. So a temperature may change, the load may change. Either of the two things happens, irradiance may change. Irrespective of all these things, my operating point should be only at maximum power. That is the idea of this total thing. So here, generally, whenever we see photovoltaic module is there. It is given to the converter and given to the load. General thing, whatever we see, we have seen that just we invert the things and give to the load, so it can operate in a closed this one, and the MPPT algorithm can be operated to operate at maximum power. Next one is what are the devices generally we see. So devices should be a, let's say, diode which operates at higher frequency. Second one is IGBT. The arrow is missing, so don't worry, the arrow should be on the E part. It's missing. So here it is an IGBT diode or any self-commutated switch. It can be a MOSFET also, but whenever we use for inverters and all, generally we go for IGBTs. Whenever we are operating at a higher frequencies, then we can go for MOSFETs. Then we can go for MOSFETs. So here this is the thing about the switches. Everybody knows this circuit, buck converter circuit. So if I have a solar panel, if I have a switch, so I have not drawn any switch. This generally switches are MOSFET switches, because MOSFET switches operates at 100 kilohertz. 100 kilohertz operation means very high switching. MOSFETs are generally used in DC-DC converters for solar applications. So here, whenever I switch on this one, what is going to happen? So power supply from here, it goes to this. So through the load, so capacitor holds the charge and makes the voltage constant at this point. And whenever I remove the switch, whatever the energy stored in the inductor will be having a freewheeling action through this diode, so that the load current will not fall to zero at any given point. This is the thing. So here, this is the general buck converter where you can see in Rashid, Nedmohan, or any of the, let's say, PS Bimbra. So any of the polytronics books, we can see find such a circuit. So here, but here we don't want such circuit. So what is happening is, we are, whenever you go back, whenever I put on the load, what is happening? For this circuit, everybody knows that any DC converter, DC-DC converter gets from fixed DC voltage to a variable DC voltage. What is a fixed DC voltage? If I have 100, the output can be either less than 100 or more than 100, whether if I am using buck converter or boost converter, but the input will be always less. Input will be always fixed, but the output will be changing. But whenever I look into the changed circuit, this is the solar panel. The capacity has been shifted to this point, and the load is no more a capacitor load, but it is a battery. Battery means what? It is a fixed voltage circuit. So what is the change in this? Earlier, here was the capacitor. Earlier, this was the inductor here. So now what is happening? The capacity is being shifted. Now what is happening with the circuit? Whatever you are seeing, as soon as I switch on this one, this part, output part, will be fixed. Input part voltage is going to go down, going to come down. Whenever I open this one, this remains same, but this voltage is going to go up because there is no load on the solar panel. Means what is happening here? The input voltage is variable, but output voltage is fixed. For our particular application, we require some, let's say, some circuits where input part should be variable, but the output part should be, output voltage should be fixed. So here, whenever I switch on, immediately the voltage is going to come down because the load is there. The load is what? The current flows to the inductor and battery. And whenever I remove, what happens? The inductor voltage flows to the battery and lose the freewheeling action. The capacity has been shifted to the solar panel side. Okay. So this is the change, whatever we are observing. What is this algorithm is about? This is called, many algorithms are there, which is called perturb and observe, and also called hill climbing algorithm. Climbing is what basically, whether we are climbing the PV curve or coming down the PV curve is very interesting for us. So what we do is, so here, whenever I am going to, here, what we do is, we sense the voltage and current. We find the power, and we compare the this instantaneous power with the previous instantaneous power. So what happens if the value is 0? this instant in power and the previous sample instant in power, the power both are same, it indicates what? You are on the flat portion of the curve, you are on this portion of the curve, this portion, because it's a flat portion for some amount of period. So if the instant previous, this instant power and the previous instant power is just equal to 0, then immediately we'll come to the update and return. Example, I'm going up the hill. Up the hill means what? The previous instant is less than the present one. Then what happens? This will be like this. Then what happens? S will come down this side. If example we are on the other side of the hill, other side of the PV curve, we immediately understand that the previous, this is my, this one, I'm going down, and next one will be lesser than this one. So what happens? This will be negative. This value will be negative. No will come to the other side. So what happens? Whether the previous power is less than the present power, or previous power is more than the power, present instantaneous power, decides whether I'm going climbing the hill or coming down the hill. So then what happens? The duty cycle of the converter should be either increased or decreased. So increased or increased is mentioned by what? Whether I'm increasing the voltage or decreasing the sample time. We'll check from these two rhombus blocks on either side, and whether it is required to increase the duty cycle or decrease the duty cycle will be decided by these two. And every sample time, every sample is what? The samples are being generally taken at the instant of 1 microsecond. 1 microsecond is 1 into 10 to the power minus 6. Every microsecond we take a sample, we compare for power, we compare for voltage, we'll check whether we are climbing the hill, we are going down the hill, whether to increase the duty cycle or decrease the duty cycle. Then we understand this is the basic understanding of MPPT algorithm. Whenever I was learning the MPPT algorithm, I was always feeling this algorithm is something where we cannot solve it. It is looking like some block diagram. Whenever I solved it, whenever I could solve this, I thought this is the simplest which can fit into a small block of things to get the things. If I have a solar power and all, to write this thing or to apply in a Simulink model, it's very small. So why we should do this? So here we already gone through this. This is the point where the maximum power is going to occur. So we are going to operate in this. So the previous topic, whatever we spoke about, is on the basic thing is what? Solar panel, how the irradiance, how the things are happening, how the things should be operated, how the loads are should be there so that we should operate maximum power. The next thing is what? Whether we use the buck converter, we reshape the buck converter, and we gone for a P&O algorithm. That is the previous work. Now next one is what we are going to apply for. We study the D-STATCOM because we study the solar panel, we studied the D-STATCOM. If we interlink it, then we are going to get the whole things. So what is harmonic in this one? This is a sine wave of fundamental frequency 50 Hz. If I add a third harmonic to this, what is going to happen? If I add this third and the fundamental harmonic, the combined waveform looks like a bump in the sine waveform. It looks like a bump in the sine waveform. If I add the fifth harmonic, which is 5 times the frequency of the fundamental to this, what is going to happen? So it is going to happen is the fifth harmonic, the waveform will, which is now, if you see, this waveform is consisting of fundamental, third and fifth. Now, if I add the seventh also harmonic to this, if I add seventh harmonic, the waveform looks something like this, and the things are going to look something like this. And if I go on adding, at last I find that going on adding the harmonics, I'll get a square waveform. Nowadays, whatever the polytronics devices we use, it is in shape which is not in the form of sinusoidal waveform. But if I apply the Fourier analysis, I understand that any periodic waveform is a no, I'll say not a sinusoidal waveform, is a combination of many sine waves with a different amplitude, different frequency. I'll get this one. So this is one inverter output or that which rectifies input current waveform. You can see you can study like this. You have analysis in Rashid also, or it is by MS Rashid. This is a D-STATCOM. D-STATCOM is what? We have a source impedance, and we have a load, and we have a point of common coupling PCC, and we have small interfacing inductor. We have an IGBT. This is a three-phase D-STATCOM, and on the DC link we have a capacitor. Whenever you look into all this, what is understanding is, if the load we draw is a square waveform, but all of us require a sinusoidal waveform at the grid, because if I have non-sinusoidal waveform at the grid, if the same waveform is being drawn from the grid, this has to be drawn from where? This has to be drawn from the either Warangal, either Nagarjuna Sagar, either Kottagudem or Srisailam. So where it is a machine only, it is an alternator. If I draw some waveforms like this, what is going to happen? It draws lot of harmonics. The generator has to be derated. Lot of heating effects will be there. Sometimes it may burn the total system also. It may burn the total system. That's why what we do, that's why we study a D-STATCOM, where even if I draw a square waveform also, I have to get a sinusoidal waveform at the grid, because this D-STATCOM is going to inject currents in such a manner that it injects all opposite harmonics into the line. So harmonics, it gets cancelled out. Only the fundamental is being seen at the grid side. So this is the thing. So here, whenever we see, there are some control algorithms for this. Whenever we study D-STATCOM, the basic algorithm, I'm not going to see this, but I'm going to study this. What is this algorithm is? How this algorithm will look like? Here, whenever we see, this is being inspired from SRF theory, synchronous reference frame theory, which you can see at the top of the, let's say, algorithm name is, this is inspired from the machine subject. In general machine theory, we can study synchronous reference frame, where we convert ABC into DQ0. ABC into DQ0 components, where we generally find the load currents are being sensed and converted from ABC to DQ0. Here D and Q are being seen and not taken 0, because I am assuming that the positive and negative signs, also positive off cycles, are same. So I'm not going to take any 0 component in this. I'm only going to take the D and Q components. And what I'm doing, whenever I convert, because load currents are highly nonlinear in nature, what I'm going to do, whenever I do here, this ILD and ILQ are not going to be very, I will say, analog quantities. We have to filter it out with a low pass filter. Then I'll get almost a DC component type thing in this one. So what I'm getting, this DC component measures the active component of, I will say, load currents, and this IQC gives us the reactive components of the load current. What I have done, so for doing this, how can we measure this? We require some theta for this. Theta is what? Sin theta and cos theta. What is the angle between the load currents and the voltages? So what I am measuring is, the 3 currents are measured at the point of common coupling given to a PLL. PLL was 3-phase lock loop. This measures the sin theta and cos theta, and sin theta and cos theta is given to the Parkes transformation. Only these load currents can be converted into the let's say DQ0 components. And DQ0 components, 0 I am not taking, only D and Q I am taking, filtering it out. And so here, and again this say sin theta and cos theta I am also giving to the inverse Parkes transformation. Inverse Parkes is what? Again DQ0 is converted into ABC. So you may ask me, sir, where is, you are not taken 0 here, 0 here and 0 here. I'm also giving 0 for this also. 0 I'm going to give here, so that I'm not going to consider the unbalance in the positive negative cycle. So here, up to this point, it's okay. Why we are converting this? So here, whenever we are applying the PI controllers and all, PI controllers, the DC bus, if I go to the previous slide and all, this STATCOM is going to operate in very good condition when the capacitor voltage is exactly more than the peak value of line-to-line voltage. There is a theory that there is a design aspects where this capacitor voltage should be larger than the peak value of line-to-line current. Just peak more than the peak value, but we are not going to take any risk. Peak value is 1.414 times the line voltage, but for the sake of convenience, the researchers have taken 1.65 times the peak value of the line-to-line current. Okay, so here, this is the thing. So what I am doing, the DC voltage, if I'm saying that it is not more than the 1.645 times the line-to-line voltage, I measure the DC voltage, filtered it out, compared with this, I got an error. I'm saying that I should get 700 volts here, but I'm getting only 600. Then what happens? 700 minus 600, I'll get 100 volts. This 100 volts, what happens? 100 volts is being amplified with the PI controller, and I got a loss component, and I'll add to this. What happens? Now the grid power will flow into the capacitor side. The capacitor voltage is going to increase. Example, I'm saying already the DC voltage required is 700, but the DC bus voltage is going as 800. Then what happens? This is 700 minus 800, I'll get minus 100. So what happens? The capacitor voltage should be decreased. Why should it be decreased? If I go on increasing capacitor voltage 1 point, there is a rating for a capacitor, and this rating of the capacitor is more than the, if it goes more than, the capacitor will burn out, and it is a very costly affair. So what happens? Whenever it is there, automatically it will subtract the I loss component. So what happens? The capacitor will be feeding the extra power into the grid. So what we are doing? If the DC bus is larger than the reference one, capacitor will feed to the grid, and if the DC bus voltage is less than the reference, then what happens? Grid will be supplying to the capacitor. This is the basic idea of this block. And coming to this side, I measure the voltage. Many times you see voltage regulation we talk about. We talk about many things like voltage regulation. Voltage regulation is what? Whenever we measure 415 volts on three-phase line, we should get 415. Anything less than that, example, I'm getting 400 volts. I say 415 minus 400 divided by the value, I will get regulation down or regulation up. So what happens? Nobody likes the voltage should be fluctuated, because many places, sensitive places like hospitals, scientific equipment, work on exact voltages. Even the voltage is more, voltage is less. The only thing which will happen is the equipment may burn or equipment may not operate properly. So what I'll do is I measure the voltages, convert into the terminal voltage, and what is the exact 415 I want, I'll give it to this, because we all know that according to our machine subject and all, if the voltage falls, that means what? Your inductive load is more. If the voltage increases, the capacitive load is more. We can study from Ferrand effect as well as the machine subject also. So whatever the error is there between the reference 415 and the exact measured one, it will give to the PA controller, and we are going to give to the quadrature line. And what happens when I compare this, the loss component and whatever the regulation component is being added in D and Q components, again I'll invert it. Now I'll get the source current ABC. That is the actual things what I require. What is the actual things? But what I am getting, these are the actual things I am getting, sensitive things. This is the ideal things I want. These are the sense things. So what I'll do, I'll compare this one with the sensed one. I'll give to the PWM converter. Whoever knows about the D-STATCOM and all, this is the basic algorithm. Almost many of the people might have solved, because it's the first evolved algorithms, SRF theory. So this is the basic algorithm, whatever we study. Now in the previous slide, I gone to two PA controllers. And I know what is the KP value and KA value. So nowadays what they are doing is they are applying the PSO technique, particle swarm optimization technique. So particle swarm optimization says that what initialize the KPK values, find the fitness function, get the P best values, P best and G best from this, and so we written a small code for particle swarm optimization and linked our also linked our Simulink blocks. Then we could get two things out of that. If I just plot this one, I could get what is the ACPA controller gains, 2.72 and something like 3.35, something like that. And whenever I run this algorithm, I could understand that 1.5 is the KP value and approximately 0.5 is the KA value, because right side green line is the KA, this one blue line is the KP1. And if you just plot, what I understood is nowadays whenever we generally see, we are not going to get the exact value, but by this algorithm we are getting the exact KP and KA values. And this is the convergence, how fast the values are being converged. In the third iteration we are going to converge the KPKI values. That's why we use this algorithm only to find nothing to do with the solar panel, nothing to do with the D-STATCOM, only to find the exact KPK values of the PA controller of the D-STATCOM algorithm. So how I convert SRF algorithm? SRF algorithm can be, also the Parkes transformation is what? The load currents are being converted by set of equations. The set of equations can be found in any of the research paper. No need to understand this. And the DC bus also comparison, the PA controller equation in digital form, and how the additions are being done. These all are basically from the block diagram which I shown in the also SRF algorithm. So this is the inverse Parkes transformation. This is the way how generally it goes. And DC link voltage is being given by some formula. This also you can find in any of the research papers, sometimes in books also. And this is the LF filtering inductor between the point of common coupling and the D-STATCOM. This also LF values can be calculated. Capacitor value can be calculated. DC bus capacitor can be calculated by this formula. And ratings, how the ratings can be done. The switch ratings, current rating and voltage rating can be designed from this formulas. So this is the way how generally we go. So whenever we go, first time when we have done a D-STATCOM in the lab, we have designed something like this. So here whenever we see the controller, whatever you see is in this block, controller, whatever the controller is there, is inside one of the slot of this computer. This is the DSO. DSO means digital storage oscilloscope. These are the two power also power supplies which we can give to the boards and all. And here also one more power supply board is there. We have one STATCOM here, STATCOM, or we can say here these are the loads, and we can see these are the LF inductors. Inductors are what LF we told, interfacing inductors. And sometimes we have a transformer also for neutral current compensation. So this is the way how here whenever we see, whenever we talk about, this is the basically the D-STATCOM what we applied in the lab. These are the power supplies, and there are whatever the processor we have taken is a D-Space 1104. So we have 8 ADCs and 8 DACs, digital to analog converters. So we have given sense this one and given inside the motherboard, inside to the computer. So these are the voltage sensors. LEM CV3 1500 is the sensor I used, and ABB EL 50 PIBB is the ABB sensor for current sensor I used. Example, if I want to measure a big system, if I want to measure the voltage, I'll connect this one, and from this I'll give to this block. From there I'll get plus or minus 15 volts. If I want to measure the current, I'll pass this wire between this also current probe, current Hall effect sensors. Automatically the current will be sensed. The sensed current will be given to the processor like this, through this. So this is the way how generally done. And this is the isolation board. During our time, one of the MTech student has done. This is the circuit diagram for this. This is the isolation. So whenever there is a fault in the power circuit, the signal can be amplified and also isolated, so that the signal circuit and the also power circuit can be isolated with each other. So whenever you look into the also just clearly, this is the work previously one of my MTech student Sharath has done this. Simulations are I've taken that simulations only. Just look into this. These are the voltages, 3 voltages. Why this is not going? Okay. And these are the source currents. If you just observe, I'm drawing a load current something like this, completely square currents, because I'm using a rectifier. On the DC link, I'm using a large inductor and in series with a resistor. Even after that, this is a balanced nonlinear load. Even after that, I am finding that the source currents are highly linear and sinusoidal in nature, and even balanced also. Even if I am removing one of the phase also, I am finding this one balanced in this. The first case I told you, when we are integrating the solar power to the thing, we are going to get something. And whenever you see the compensator current, the currents which are flowing from the solar towards the grid is looking like this, because energy is being generated. The terminal voltage is regulated, and DC bus, whatever I told, DC bus is around 700 volts, I think, or 800 volts is being measured here. And whenever you see the solar power, if you just observe the solar power, it has been fluctuating. The power currents are been fluctuating, but the voltages are almost constant, because I have taken for a 2-second time period, I think. And if you check the load neutral current, it's highly passing some currents, but the source neutral doesn't have any currents in that. So this is the nonlinear load part. Whenever we look why we should do this, because the loads may have highly also nonlinear, which is having a THD of 46.45, and whenever we look into the source current is having 3.45 and source voltage is having 2.11. So I just not noted down here. But if I have a large THD also, the THD of current and voltage are much less, which indicates that my compensator is working very well. And one more thing, whenever you see into this side, even solar power is generated, but solar power is being pumped. This currents, if you see currents, large currents are seen just to make sure that solar power being injected into the grid side. And grid side with high power quality. High power quality is what? Load balancing is there, neutral current compensation is there, and THD in source and load bill is highly sinusoidal. So this is our, and whenever we look into the, I would say, hardware diagrams, we just observe, if I have an unbalance in one of the phase, but the source is having a balance, 7.54, 7.56, 7.53, almost balanced. Voltages are 415.8, 415.9, 415.9, and the frequency is around 50.2, 50.2, and something like that, which is very near to 50 hertz. This shows even my load currents are unbalanced, but the source is balanced. And by this, seeing these three, I would say, waveform, 6 waveforms, it is understood that it is highly sinusoidal, and as well as the THD is under control. And whenever you look into this, here, if you just check the power source, if you just check into this, what is the THD in this case? 2%. And what is the THD of the voltage? 4%. But the load is having a THD of 21.8, because in hardware you cannot get a large THDs and all because of large inductance of the inductors and all we use. In simulations we generally get it. And whenever you see in this two bottom diagram, we see minus 5.37 indicates that power is not feeding from grid towards the solar, but it is feeding from the solar towards the grid. This is the thing. And whenever you see the last one, this is the VDC, this is the solar voltage. If my irradiance is being increased, so what is going to happen? My current is going to increase. And in the second case, if irradiance is decreased, the solar power is being decreased, automatically the solar power is increased, the power, I will say the voltage, the currents which are at the VSC are increased. If it is decreased, what happens? The VHDs are decreased. From the bottom things, we understand that even the load is removed, the source is balanced. Whether you're removing the load, you're putting back the load, both sides you find that we'll say it is a balanced, and whatever the issues what we are going to get. So here a prototype inverter D-STATCOM of three-phase distribution system for solar applications has been implemented with unit template as well as SRF. I only explained SRF for you, and all the THDs are less than 5%, which is absolutely according to IEEE 519 standards, and the results are satisfactory. And the also load perturbation, wherever the load changes are there, still the controller is acting as a stable controller. These are the conclusion, and this is the thanks from my side. Once again, we'll go back and I'll take 5 more minutes. So what we have taken from this? Now you'll understand what is the exact thing happening at this point. So here, up to this point, this is basically a D-STATCOM. The first part, this one, solar and MPPT algorithm explained. And on the DC bus, we observed a small buck converter where this DC can be changed to any level like 24 volts, 48 volts, 72 volts, and given to one small cable which can used for charging of the electric say cars. So while doing all this, while pumping the power to this, the solar power can be pumped into the DC bus. DC bus is always also maintained at particular point. What it is happening? This is just maintaining the DC bus constant by the algorithm, and the extra power is being fed to the grid. So what is happening? The solar power is also feeding to the grid, also charging the electric vehicle, and the power quality is also being maintained. These are the conclusion of the today's lecture. Any doubts you can ask me, so we can so 4 things we have addressed.
Some questions are there. I'm reading
Okay,
out,
please.
sir. What is the difference in operation of buck and boost converter? Are these used in DC to DC converters in electric vehicles?
See, our application is what not directly into a I would say battery charging applications. Example, if I have a DC power, I'm at a charging station, then what I'll do immediately, either I'll if I have more voltage, I'll do a buck operation and give to a 48 volts electric vehicle. If I have the voltage is less, I'll go for a boost operation, give to an electric vehicle. Either of the two things I'll do. Our work is what? Many times we go into the solar applications, because nowadays, if example tomorrow's date, we have a lot of solar panels in our society, and we want to give it to the grid also. Then even we want to have, even we have a own car in our home, electric car, we want to charge it. So what I'll do, I'll just take from, I will say, our whatever the supply we are getting in our home is single phase supply only. The same formula can be applied for single phase also, but I'm saying that it applies for whether I'm boosting the voltage or by example, I'm saying that in the evening time, maybe I'm saying in the evening 5 o'clock or 6 o'clock, now whatever the time happening, the solar irradiance are very less. What happens? The voltage generated on the panel is very less, but I want to have more voltage on the DC bus. Then what I'll do? More voltage on the DC bus, I'll go for a boost operation. But example, if I have in the noon time, the voltages are very high. then what happens? I have to go for a buck operation so that I'll give it to a DC bus. Depends on which in the night time there'll be no solar irradiance at all. Then what happens? Neither the buck operation or boost operation is not possible at that time. So that is a way how generally we look into this.
Thank you, sir.
Okay.
Sir, another question.
And he want to start his research in this area in power electronics and drives. Please, planning for PhD, kindly suggest in which area in power electronics best to consider for doing research.
No, actually, what is the thing? Generally, any research is not. Example, you talk about me.
Yes, sir.
Example, if the PhD is of 3 to 4 years.
Exactly.
3 to 4 years. In 3 to 4 years, we generally what we'll do is 2.5 years we'll be only working on things which are already existing. We never do anything which is advanced in nature. Even myself, we at least 2 years or 1.5 years I have done all the simulation work which already previously some people have done it in the area of interest. In the area of interest. Example, I am saying that my area of interest is power quality. So I have done power quality work. If somebody is interested in drives, somebody is interested in solar applications, somebody interested in water pumping system, somebody interested in wind. Which area the student is interested is very interesting one. So what happens? That's how the papers which are connected to that. One easiest paper, the student should download it and do the simulation. When 1.5 year or 2 years, 1.5 year, he should do the previous work. Then he will come to understanding that what is the advancement. So the research, whatever we do is 100 we do the previous work, 1 or 2% we do the extension of the work. So it is not like that we just connect to some work, start immediately and get a PhD. It is not like that. So what we have done, I have done my research in hydro applications in power quality in remote areas like Nepal and all. So we have taken a small 7.5 kilowatt generators, isolated generator hydro plants, and we have controlled the voltage, frequency, and power qualities. Then immediately after PhD, I could understand that the same things can be applied for wind, same things can be applied for solar, same thing can be applied for some other places. Then I understood, oh, this is the way how the research can be progressed. It is not exactly this area. Whatever I taught today is present day work, present day which people are doing in NITs and IITs. So if somebody is interested, they can carry the work in the similar direction. Please, one more.
Sure, sir. Sir, is EV charging is used for DC link?
PV charging is
EV electric vehicle charging is used for DC.
This is an idea. I got recently 2020 IEEE transaction papers. If you just observe the things, even my work also. What we are doing is basically D-STATCOM is used for solar, I will say power quality applications. Solar is used for self-generation. If I interlink both, we got something. From that, we got an extension that if on the DC link, if I put one solar, I will say electric vehicle charger, what happens? It is working. And latest paper have seen 2020. Also, there is a very good transaction by Professor Beam Singh. Yes, people can cross-check it.
Sure, sir. Sure, sir.
Okay.
Next, what is the objective function and what is the cost function in PSO algorithm, sir?
PSO algorithm, see, I am a polytronic guy. One of my young person is there in, I would say. So what we have done is, I have not studied the complete PSO. PSO, the algorithm remains the same. I have not touched the algorithm. But what I have done, the errors which are coming in the PI controller, I have linked to the PSO algorithm through some small program. Whenever I linked what happened, whatever the errors which are occurring in these errors, if I example KP, the PSO algorithm takes some KP and KA values. instantly, and keep on going for iteration. This work can be best judged through a power system guy, not me. I have just taken the help of some power system guy and applied it to my system and got the KP and KA values. That's all.
Sure, sir.
I have not gone very deep into the PSO algorithm. I have just taken some thing, studied a limited work, applied to my phase. So here what we have done, I taken 10 iteration, 5 particles. For 10 iteration, 5 particles, and 4 also dimensions, and also KPK of DCPA control, KPK of ACPA control. This is the work what I have done. Please.
Yes, sir. Thank you, sir. And next question is, the type of charging in electric vehicles depends on what factors?
See, this is again you are entering a place where also electric vehicles. This one. So how they nowadays the batteries are changing. Fast chargings are there, drip chargings are there, slow chargings are there. You know that I think. Nowadays, if example car is going on a highway, example they will stop for at a station, and they want to charge the also vehicle within 15 minutes. Nowadays, mobiles are also coming in Samsung or all you see. The mobile charge will get charged within only 5 minutes. So nowadays electric vehicles are coming with boost chargings are also, or normal chargers are also. Depends, but boost chargers are very effective because nobody have patience. They have to get charged their vehicle within very less time. And it is a different area where I have not worked on the electric vehicles area. I have just worked on the how can it be a charging station, DC charging can be.
Sure, sir. Thank you, sir. Can you suggest, sir, can you guide us for future trending topics in power electronics?
See, example, if you ask me, what can be a trending topic? See, our fuels are going down. Fuels are going down. After some years, you'll not find any fuel further. We have to depend on either solar or wind. In India and place like our country, where the solar energy is abundant, not like Europe and all, where the solar energy is not abundant. In such cases, what happens? Renewable energy becomes a bigger topic. Wind becomes a bigger topic. Wind, solar. So some places in Karimnagar and all, biomass things are there. So where you have to think where there is a small gap in the research. So here I think renewable energy sources, connection to grid, not connecting to grid, for solar applications, for electric vehicle applications, many places you can apply this. See, whenever you are starting a research, you have to always go through some big journals like IEEE, where you find these big journals will give you an idea where the work is going on. Then you can start the work immediately there from there.
Sure, sir.
I feel I can suggest renewable energy sources is the big topic in electric vehicles, and electric vehicles are also going. Okay.
For future generation. Thank you, sir.
Yes.
Thank you very much, sir. There is one more general doubt, sir. Can we produce a virtual impedance in a system by using power electronic converters?
Virtual impedance.
Yes, sir.
Electronic converters, virtual impedance. No, I have connected the impedance outside the converter itself. I have not, we couldn't calculate any virtual impedance in the system. So what is the basic doubt? Who has asked that?
Sir, just a minute, sir. Kurra Ranjit, sir, if possible, I'll unmute you. Please, you can ask your question directly.
Okay, please.
Kurra Ranjit, sir. I'm giving the option of unmute. Please question, sir.
Excuse me, sir.
Yes, please.
Am I audible, sir?
Yes. Please, can you be move aside so that we cannot have any disturbance from there?
Yeah. Is it audible to you, sir?
Yeah, now it is. Okay. Right.
Sir, my intention is like virtual impedance mean there must be some kind of impedance created where it should not lead to any losses in the system.
But every system has some losses.
Yes.
Yes or no?
Yes, sir. Yes, sir.
Yes, sir.
What you
Yes,
said
sir.
is right.
In which system? No, where you applied this? Which system you got through this? Can you tell me?
Sir, like if I want to control the current discharge from a capacitor, for example, sir, if I want to control a current discharge in a capacitor, so by using some kind like capacitor is discharging at a very faster rate. So if I am using some kind of power electronic converters through which the discharge rate of a capacitor can be controlled, can I model some system like that by using some?
Actually, some I think 2011-12 models I've seen. I never seen virtual impedance things into my knowledge. In 2020 model, I cannot say. Really, I cannot say that. I don't know also.
Yes, sir. Okay. Thank you.
Virtual impedance, I never seen in any of the models. I have never seen it. Into my knowledge, according to my knowledge, I have not seen.
Thank you.
Thank you very much, sir. There is one more small simple question, sir. Is MPPT similar to maximum power transfer theorem?
Maximum power point tracking.
Yes, sir. They are asking the difference between means MPPT and is similar to maximum power transfer theorem, sir.
No, maximum power transfer theorem is from source to load. So it is happening that from source to load, if the source impedance is equal to the load impedance, maximum power is being transferred. Here it is not like that. Here the things are what? If I just go, can you see the screen? I think I'll just go back.
Yes, sir. Yes, sir.
Here, if I take only this much current here, what happens? The power is this much. Yes or no? If
Yes,
I
sir.
take here, the current is here, the power is this much. Means what we are saying is power is only maximum at this point where this is the current, this should be the current or this should be the voltage. Either I should operate at this voltage or operate at this current. So what we are doing is I get a voltage of 500 volts from the solar panel. But whatever we are looking is solar panel voltage is 500, but to operate at maximum power point I require 33 volts. Example I'm saying. What I'll do, immediately the DC-DC converter, the MPPT algorithm gives at what voltage and what current the maximum power is being occurred, that it will give the input. Immediately what I'll do, I'll change the duty cycle of the DC-DC converter. And what I'll do, I'll give a duty cycle in such a manner that the voltage of the output of the DC-DC converter will be 332 volts only. Voltage is 332. The current has to be this only. Because when the voltage is here on this curve, the current has to be this. So what it is happening, maximum power. After some time in the evening, the voltage might have reduced to 400. The maximum power point also has gone to a different value, like 240 volts. Then what happens? Automatically the DC-DC converter, the duty cycle is being changed in such a manner that so what is going to happen? It will operate at different point. So operate different point. So what is going to happen? I'm changing the voltage levels by DC-DC converter, finding the duty cycle by maximum power point tracking. Maximum power point theorem and maximum MPPT algorithm is completely different. There is no connection also.
Yes, sir. Yes, sir. Thank you very much, sir. Still, any of the participants, if anyone is having any doubts, you can raise your hand so that I can unmute you. We can ask the question directly to sir, or else we can place in the chat box. Right. Thank you very much, sir. Today's session enlightened us for interfacing solar PV system for electric vehicles. Sir discussed concepts are very informative to us and provided a very great ease to the participants. And the session extensively was useful for the research scholars, PG students, and also for the faculty. Thank you very much, sir, for upgrading our knowledge. With your permission, if the research scholars, those who have some any doubts regarding this electric vehicles or the battery charging, can we give the permission to them to discuss once with you, sir, at any time?
No problem. Email ID is with Ramesh sir, and my phone number is also. So they can do email ID whenever they can drop a mail, whenever they have some doubts. So I'll be available with that mail.
Sure, sir. Thank you very much, sir, for providing the permission for the research scholars and PG students who are doing their thesis work related to battery charging of grid interface system for electric vehicles can get technical inputs from sir, which in turn helps in motivating our participants as sir. Now it's time to word of thanks. I request Mr. K. Ramesh sir, Associate Professor, Faculty Development Program, to convey the valedictory of session. Ramesh sir.
Okay, sir. Is my voice is audible?
Yes, yes.
Okay, sir. Okay, sir. Good evening, one and all. Myself, K. Ramesh, Associate Professor and one of the coordinators of this FDP. I'm very much delightful to convey vote of thanks on behalf of our department. Let me express my heartfelt gratitude to our today's eminent speaker, Dr. V. Rajagopal Garu, for sharing valuable information on battery charging of grid interfaced solar PV system for electric vehicles with participants of this faculty development program. I'm sure participants would have learned more from this session, which will enhance their knowledge and professional career. It is my privilege to thank our honorable management of Vaageswari Group of Institutions, General Secretary Dr. G. Srinivas Reddy Garu, Joint Secretary D. Srinivas Reddy Garu, for boosting and assisting us for conducting this type of activities. It's my pleasure to thank our beloved principal Dr. C.H. Srinivas Garu for continuous support and encouragement for organizing this event. I also express my heartfelt thanks to our beloved HOD, Dr. M. Ramesh Garu, for providing continuous guidance and sincere efforts for smooth conducting of this faculty development program. I extend my sincere gratitude to all our department faculty and participants who helped either directly or indirectly for smooth conducting of today's session. Thank you one and all.
Thank you, sir. Thank you,
Answer over to you.
Thank you very much, sir. Rajagopal sir, thank you very much for enlightening us with a good upcoming upgrading of our knowledge for future generations, sir. Thanks a lot, sir.
Thank you, sir.
Thank you very much. Thank you.
Yes, welcome, sir. Now I would like to request all the participants that we have placed the today's feedback link, day 5 feedback link in the chat box. I request you to please collect the link from there and submit your feedback links. And please reply me in the chat box with yes, so that I can get confirmed that our link is working properly. Thank you very much for your active participation of participants. Your active participation makes our program successful. And I would like to inform you that that is the last day 6 of our FDP will be continued as per schedule tomorrow. That is from 4 p.m. to 6 p.m. And our tomorrow's resource person is from NIT Warangal. Dr. C.H. Ramulu sir, working as assistant professor in the Department of Electrical Engineering. And our tomorrow's topic is on single stage photovoltaic source fed induction motor drive for water pumping application. Hence, I request all the participants to be in contact with us with the Telegram group for all the updates, and to join the tomorrow's session also to update. That will be the last session for the FDP tomorrow. Thank you all. Thank you very much, sir. Sir, Rajagopal sir, thank you very much, sir, for accepting our invitation and joining us. And I wholeheartedly thank you for increasing, for upgrading us, sir. Thanks a lot, sir. We have learned a new...
I have given email ID in chat box, so people can Any doubts they can ask me. Okay.
Sure, sir. Some participants are asking your email ID, sir. Okay,
I'm
sir.
given
Sure, I
in the
will.
box.
Sure, sir. Thank you very much, sir.